talk. And Kat will be talking about the Arctic diffuser instrument upgrade.
Hello. Thanks, John. Let me pull it up. My name is Kadlec. I'm a research engineer at the University of Washington, and I'll be presenting on the diffuser rotation upgrade for the Arctic instrument on the 3.5 meter. So most of you know Arctic is an imager. It used to have a 6 arc minute field of view, but they improved the baffling to be a 7.8 arc minute field of view. It has a filter wheel and the diffuser. It can be pneumatically actuated and creates a 9 arc second full width half max when used, using the diffuser's 0.34 degrees opening angle. As you can see in the red rectangle is the diffuser mount on the front of the instrument, and I'll discuss why that's there later. And that you can see the black area, it inserts into the beam path and then exits out of it. So I'm not going to talk about the photometry part too much because that's not what this is about, but the diffuser adds diffusion, and the more diffuse it is, it creates a larger PSF and lower intensity at each pixel. So this allows for better averaging with the interpixel sensitivity, and you're able to increase for longer exposures, so you don't have to worry about detector saturation, and you don't have to worry about, well, it gives a stable PSF. And the main goal of this upgrade is to provide an even smoother PSF by rotating the diffuser. So the initial diffuser design was a late addition in the design process. The first design, that's why it was mounted on the front of the instrument. The initial design had an impeller drive, so it was all pneumatic, and it had a homemade bearing with no sensors. And the problem with this one was that it was the bearing was binding, and so a second iteration was made, and this one used a V-belt drive, and unfortunately the V-belt had a high friction, so they had to have a large motor, and this motor intruded into the NA2 port, and it also had lubrication and issues with the fitting inside the housing. So this had problems and had difficulty rotating also. So that brought us to V3, and talking to the photometry science team, they came up with 120 to 180 RPM of rotation speed. And this is a somewhat simple requirement, but it also has requirements on the mountain on the instrument with interfacing with the telescope. So it has to minimally intrude into the NA2 port, so no large motors, and it has to work safely, reliably, and be maintainable. So it has to have proper covering, and then having sensors, so telemetry for when the cover is installed and when the diffuser is up or down into the beam path, and then an RPM sensor to make sure that it is spinning at the correct speed. So we decided, we wanted to go with some certain improvements to the design. We wanted to go with a round belt drive and a brushless DC motor, and it's much smaller. These are quieter and smoother, and they have low friction, since we don't need a high friction V-belt because we're not too worried about slip and power transfer, since we're just spinning the diffuser. And you can see it's only a ½ inch above where the base is. We use the same bearing as the V2. We were able to clean it out, and we feel that the fit can be fixed, so that way the material mismatch doesn't cause binding. We also added Hall effect sensors. These are boards that detect magnets, So by placing a magnet on the assembly, we can use it to sense when it's in motion. And then also maintainability. We added a lot of lubrication to the important things like threads and bearings, and we also added covers for safety and also for longevity. So this is the main diffuser assembly. We used the linear base. We felt like this part worked fine. It has the middle part is the black rectangle. That's what the main upgrade to the assembly, whereas the gray part is the same as from before. It has a pneumatic actuator and linear slides and linear bearings that we've kept the same. We did add in and out Hall effect sensors, so that way you know when it's in and out of the beam path. So this is the diffuser table. In the middle, you have the rotating diffuser. It's held in with retaining rings and a spacer. This is mounted into the inner race of the bearing, and this assembly rotates on the bearing. The bearing is coated with a synthetic oil we found to have low viscosity to keep the motor torque low. And then it also has very good temperature properties. So at low temperatures, it keeps its low viscosity, so it doesn't clog up the bearing, and you're able to rotate even at the low temperatures at APO on the mountain. And this pulley has a pulley ratio of 3.5 to 1, and it can be tensioned using with adjustment screws. So this is an exploded view of what the diffuser looks like. You can see the bearing is the ring, and the optical housing gets installed into that inner ring. It's close to transition fit. And then that goes into the housing, and that's a clearance fit, which allows for the thermal expansion and allows to not put eccentric loading on the bearing because of the bearing is very thin and it's very large. And so it has a lot of small bearings and it can easily bind. So we had to be very aware of that. And the retaining rings also have covers which prevent dust from getting in and any lubrication from getting out. So on the right, you can see how the retaining rings hold in the inner and outer races of the bearings, and they have the covers. And then on the left, it's the assembly for the optical diffuser. So the diffuser gets installed first, and then a Teflon spacer to distribute any of the retaining ring loading. Then there's 2 retaining rings. The first retaining ring holds the diffuser in place, and then the second one is a lock retaining ring, which prevents any backing out. And these are lubricated with anti-seize. We would have gone with usually anti-seize has some sort of copper additive, but we were worried that if it got on the diffuser that it would be an abrasive when we tried to remove it. So we went with a lithium grease with Teflon. And then you can see the 4 magnets that are glued into the diffuser that act as sensors or as magnets for the HED sensor for speed. So in terms of the electrical and software, the initial design had a shutter, used the shutter PCB to control the diffuser wheel, the diffuser. But we are going to switch to the filter wheel PCB, which will allow the shutter to go to its original function. And then we will be adding a new PCB, which will monitor the Hall effect sensors and provide control. And then there will also be a power supply added to the electrical box. And this is a pretty good amount of stuff. And fortunately, it will all fit apparently barely into the electronics box on Arctic. And you can see the 4 HEDs that will be added to the diffuser and some of the magnets on the side that will provide the sensing. Oh, and then in terms of software updates, most of the functionality is already in TUI. So we're pretty confident that it should be pretty simple when it comes to updating the updating TUI for this this upgrade. So the installation, we shipped this to APO end of last year, and unfortunately, due to COVID, there was a 25% staffing at the mountain, and this meant that only a few people could be there at once, and they had, they have normal job stuff going on, and so they weren't able to get on this diffuser until earlier this year. And unfortunately, there were some design changes that needed to be made, so they sent it back to UW, and these improvements were implemented, and it's ready to ship out again. So the plan right now is for it to be installed between August 23rd and 27th, when there's a gap in the use of Arctic. And that's the assembly as it is in the lab right now. Some of the electronics are not on there right now because they're at APO, but yeah. And I'd like to thank Ed, Rishi, and Connor for a lot of the engineering. They helped out a lot in terms of getting it ready. And then Gumi, Leslie, and John for helping out with the requirements for the engineering team, and then Sarah for helping manage, and then the APO staff for helping with delivery and installation, and ARC for the funding. Lastly, I just want to say I hope this diffuser upgrade will provide quality photometric data for ARC. Thank you.
Thanks, Cal. It's a great talk. Let's see if there's questions. There's no questions yet on Slack. I had two questions. I'll ask the first one. You mentioned that you'll be monitoring the RPM. Is this something that can be tuned?
So I think they want to limit how much is changeable. So right now we have it set to like a certain range. Is RPM good? So I think 120 to 180 RPM. But it probably can be changed, and right now the functionality is set to be just RPM good or RPM bad.
Be something static. Okay.
Yeah.
No, it was just a question because, of course, to my knowledge, no other diffuser has this rotation capability. So after non-stop, we might find something that's more optimal. And I also wrote down the availability date or the install date of August 23 to 27. So
yeah,
we look forward to using it in early September.
Yeah. Hopefully.
No pressure.
Any other questions for Cal? Nope. If not, please watch the Slack space because there's been a bunch of questions coming up for these mutation talks. And we'll let's thank Cal again, and then Derek, if you want to load up your talk.